Hello everyone, welcome back to Algebra 1 with Miss Betsy. I'm glad that you're here with me for yet another lecture. We're starting something new with this lecture. We are in Chapter 7. We're talking about systems of equations and inequalities, and what we're going to be doing here is solving two equations at the same time. Finding out what the set of ordered pairs is, or what the one ordered pair is. It's actually a solution to two equations at the same time. Now, if you're using the same textbook that I am using Algebra 1 for Christian schools. It is published by Bob Jones University Press. I'm using the second edition. You don't have to use the same text I am. You solve simultaneous equations with pretty much the same way, no matter what text you're using. But this is the very introductory teaching. All we're doing is using graphing of specifically manipulated equations so that you can solve these systems graphically. Before we get started, can you tell me what it is? I'm looking for my lame joke. What do leopards say after lunch? I said, oh man, but that really hits the spots. So, without further ado, we will continue with section 7.1, page 272 in my text, solving systems of equations graphically. Up to this point, what we've been doing is we've just worked with one equation at a time. We learned how to graph an equation of a straight line with on the Cartesian coordinate system. We learned how to graph a point on a number line. We learned how to graph an inequality, linear inequalities, where you would graph the equation of the line and half of that graph would be a part of the solution while the other half would not be. What we're working with now is finding a solution to two equations at the same time, two equations in two variables, and this is called a system of equations. And in order for an ordered pair to be a solution to a system of equations, or to two equations at the same time, that ordered pair has to come up with a true expression when substituted into both of the equations at the same time. So we have a system of equations. We have x minus y is equal to 9, and we also have 2x plus y is equal to 9. This is what we call a system of equations. It's simply two equations that we want to know, is it true that 11, 2, the ordered pair, or the point 11, 2, is that a solution to this system? Meaning, will 11, 2 work in both of these straight lines here? Well, let's see. If x is 11 and y is 2, substitute that in for our first equation, and oh yeah, looking really good, aren't we? Well, what about this? 2 times 11 plus 2, is that equal to 9? Well, no, obviously it's not. 22 plus 2, 24, is not equal to 9. So, while this ordered pair works in one equation, it doesn't work in another equation. So, let's see what we can do now. Let's see if perhaps the ordered pair 6, negative 3 is a solution to this system of equations. 6, negative 3. What happens if we substitute this in? 6 minus a negative 3, is that equal to 9? Yes. So here we have a second point that solves this first equation. Let's see what happens with our second equation. 2 times 6 plus a negative 3, is that equal to 9? And yes, 12 minus 3 is equal to 9. So we see that the ordered pair 6, negative 3 is a solution to this system of equations. Now, there are actually several different ways that you can find the solution to a system of equations. And I'm looking for my cap for this marker. I guess I will find it probably when I'm done with the lecture. There are several different ways that you can use to find the solution to a system of equations. One of them being that you could just simply keep trying ordered pairs until you found one that fit both equations. But let's think about this. How realistic and how reasonable is it? Well, when you have the graph of a line, and equations in two variables are nothing but the equation that represents a graph of a straight line on your Cartesian coordinate system, well, there are an infinite number of places on that line that you could come up with as an ordered pair. But if you have two intersecting lines, how many places is it going to both be true? It can be true one time. So it's just not practical at all to use this methodology to come up with the solution to a system of equations. This problem was very carefully constructed so that you would be able to do that. But what a much more realistic, much better idea is going ahead and graphing both lines, the equations of both lines, on the same coordinate system and looking for the point where they intersect. So let's do this. We have solved the system x plus y is minus 2, x minus y is 4. X plus y is minus 2, x minus y is 4. Now let me check and make sure that I've copied these correctly. X plus y is minus 2, x minus y is 4. So yes, what we're going to do is graph both of these equations on the same set of axes. How are we going to do this? Remember, back to last week, if you want to graph the equation of a line and you can put that equation of a line into slope-intercept form, it's very easy to graph. So first, we're going to say x plus y minus x is equal to negative x minus 2. We subtract an x from both sides of the equation. Y is equal to negative x minus 2. Now it's going to be very easy to graph this, isn't it? Because we know the y-intercept is negative 2, and we know that this has a slope of negative 1, so it has a gentle downhill slope. First, we're going to plot our y-intercept, which is at the point where x is 0 and y is a negative 2. And I'm looking at this grid, and I forgot to label these two. Let me go ahead and do this right quickly. 4, 5, and negative 6. Let me label this one. Negative 1, negative 2, negative 3, 4, 5, and 6. Our slope is a negative 1. Our vertical change goes down 1 over 1 unit to the right. So here we have the graph of our first equation. Go ahead and connect the dots. Now you want to go ahead and label this with the original equation. X plus y is equal to a negative 2. We can go ahead and label our points. X is 0, y is negative 2, x is 1, y is negative 3. Now, let's go ahead and graph our second equation on that same set of axes. So what do we have to do? We have to solve for y once again. X minus y plus y, whoops, I'm sorry, x minus y minus x. because we are solving for y. So we have to subtract an x from both sides of the equation, minus x plus 4. And you have negative y is equal to a negative x plus 4. Don't care about a negative y, that needs to be positive. We're going to divide both sides of the equation by a negative 1, negative 1, negative 1, negative 1, and we have y is equal to x minus 4. This right here is the slope-intercept form of the equation x minus y is equal to 4. It has a slope, has a y-intercept of negative 4, and it has a slope of a positive 1, up 1, over 1. Going to go ahead and connect the dots. I want you using grid paper and a straight edge, being very careful to make your sketches very nice and neat. Label the graph. X minus y is equal to 4. We're going to look at our point of intersection, and here we can see the point where those two lines intersect. It's at the point x minus 3. I'm sorry, x is 1, y is a negative 3, is the solution. Now, whether you choose to write it on the grid is all right, or if you just want to write at the bottom of your work and say that the solution is the ordered pair 1 and negative 3. So see, that's an example of why it's so nice to be able to go into slope-intercept form, and where you see that sometimes a picture really is worth, what is it, picture's worth 1,000 words? We could substitute from now until a long time from now and never just accidentally hit upon the ordered pair that's the solution to this. Okay? It's really pretty cool. It's very straightforward. So this ordered pair is a solution. Now, how do we want to make sure? Remember, I've talked about how important it is to verify things. Just substitute in 1 plus a negative 3. 1 minus 3 is equal to negative 2. It works. What about here? 1 minus a negative 3, is that 4? Yeah, 1 plus 3 is 4. So once you get your ordered pair, make sure that it works. Take the time, whether you actually physically write out the solution, your check, or whether you just verify it mentally. Take a little bit of time and make sure that you have the ordered pair verify that it's a solution to both of your equations. Let's go ahead and move on to page 234. Let me do another example for you. Long about now, you should be getting to be quite old hats at putting an equation with an x and y variable into slope-intercept form, because you do it all the time, and you'll always do it all the time with your math. With your algebra, x plus y is 5, 3x plus y is 7. X plus y is 5, x plus y is 5, 3x plus y is 7. X plus y is 5, 3x plus y is 7. What do we need? We want to find the solution to this system of equations. Sometimes some of your books will put parentheses, will put a brace around it to indicate that those two equations are together and that you want to find a solution to both of them at the same time. So let me go ahead and rewrite this one in a different color. 3x plus y is equal to 7. How do we solve these? We're going to graph both of these simultaneously on the same set of axes, x plus y minus x is equal to negative x plus 5. I've subtracted an x from both sides of the equation. Y is equal to negative x plus 5. Now I want to go ahead and solve the second equation for y. 3x plus y minus 3x is equal to negative 3x plus 7. Remember, on your right-hand side of the equation, you want your expression containing the x to come first because we're putting this in the slope-intercept form. We now have y is equal to a negative 3x plus 7. We have the slope-intercept form of both of these two equations. So now we want to go ahead and graph these on the same set of axes. Y is equal to negative x plus 5. The y-intercept is the point 0, 5. The slope is a negative 3. I'm sorry, the slope is a negative 1, so it's a gentle downhill slope. Down 1, over 1. We can now connect the dots, and we have the graph of our first equation here. Take care when you're graphing these because you want to be able to read the solution off the graph. Now, our second equation is y is equal to negative 3x plus 7. So the y-intercept is way up here at the top. And what's the slope? It's a much steeper line, negative 3. So we go down 3, 1, 2, 3, over 1. You already see where our intersection point is, don't you? Let's go ahead and connect these. You would label both of the points, both of the lines. Y is negative 3x plus 7. Our first graph, y is equal to minus x plus 5. The point of intersection, the coordinates of the place where those two lines intersect, is represented by the ordered pair 1, 4, and that's the solution. How do I check this? Well, whether I do it mentally or actually substitute this ordered pair into both equations. X is 1, y is 4. Does that equal 5? Absolutely. 3 times 1 plus 4. Is that equal to 7? Yes, 3 plus 4 is 7. So what you've seen here is two examples of obtaining a graphical solution to a system of equations. Now, let's step back and think. Now, is this going to be a method that works a lot? A little bit? Half the time? What do you think? Well, did you notice that these equations were very carefully constructed to make sure that these two lines intersected at an exact point? Where it was exactly 1 and exactly negative 3. Could have been 1 and negative 2.99987 that they intersected, and you'd never be able to read specifically enough off grid paper an actual intersection unless you had something specific. So in real life, graphing two lines on the same set of axes is not the best solution to find, not the best way to find the solution to a system of equations. but it works really well just to introduce to you, hey, I can find an ordered pair that is the solution to two separate equations at a time. Now let me look right here at the bottom of page 274. They've written out for you what we've done. Step number 1, if you want to solve a system of linear equations by graphing. What are linear equations? Linear equations are equations that, when they graph, they form a straight line. They have the form, the general form of the equation of a line, of a linear equation, is ax plus by is c. You have y is equal to mx plus b, which is the slope-intercept form. You have y minus y sub 1 is m times x minus x sub 1. These are linear equations. This is the general form of the equation of a line. This is the slope-intercept form of the equation of a line. This is the point-slope form of the equation of a line. So what's a system of equations that we're talking about here? A system is two linear equations, two equations of a line that you're going to solve at the same time. In other words, what we're looking for right now is the place where those two lines cross. So first thing that you do, we wrote those equations, each of those equations, in slope-intercept form. Then we graphed each line separately, obviously, but on the same set of axes, and you could actually read off and identify the ordered pair that marked the point of intersection between those two lines. And then finally we took the point of intersection, 1, -3, and we checked it in our original equations to make sure that they both work. 1 minus 3 is a -2. 1 minus a -3 is a +4. And that's what you need to do to be able to graphically solve a system of linear equations. You need to be using grid paper, you need to use your straight edge, you need to be precise and careful with your work, okay? That's all I have for today, and I'll see you next time.